Hello everybody, and welcome back to the continuation of page 8 in the workbook. In this video we'll look at example 1, and this is going to be our first example of a vector space. Okay, so they're giving us a set called Rn, and the set looks like a set of so-called n-tuples. That may be a new term for some of you, but an n-tuple is basically just a word for this thing that I'm underlining. Okay, it's like an ordered pair, only it has n components. N may be bigger than 2. Okay, so we're making the claim that this is a vector space. If that's really true, then there should be two operations that we can specify, vector addition and scalar multiplication. So we need to specify how those are defined. Okay, so let's do that. So addition and scalar multiplication are defined component-wise. Okay, what do we mean by that? Well, let's take just an example with a small value of n, with n equals 2, just ordered pairs here. So component-wise addition just means that if you take two ordered pairs and add them together, you're just going to add the two components separately. So in the first coordinate, we'll take a1 plus b1, and in the second coordinate, we'll take a2 plus b2. There's our definition of vector addition, okay, in R2. And then similarly, scalar multiplication, we want to take a scalar c and multiply it by an ordered pair a1 and a2. We'll just take the c and multiply it through. So we'll get ca1 and ca2. Okay, and it turns out that the set R2 is a vector space using these two operations. If we really wanted to prove that that's the case, we would need to go through and verify that the addition and the multiplication that we just defined satisfy all 8 of those properties. That would be pretty tedious to do, so we're not going to go through the details. From here on out in the course, you can just assume that this is a vector space and use that fact. Okay, well, maybe another comment that we could make here. If this is really a vector space, then there should be a 0 vector. Okay, that was VS3 on our list up here. So what would the 0 vector in R2 be? Okay, well, to figure that out, ask yourself, what would we need to add to A1, A2 to get A1, A2 back again? Okay, well, 0, 0 would be the thing that works here, just the way that we defined addition. So what we've just confirmed here is that the ordered pair 0, 0 is the 0 vector in this vector space. Okay, so notationally we could write this as 0, 0 equals the 0 vector. Remember that notation, 0 with a v means 0 vector in R2. Okay. Now it's convenient in this particular vector space to be able to visualize vectors, okay? And so this is something that you might remember from previous courses. Geometrically, vectors in Rn can be thought of as either points or arrows. Okay, I want to just do a quick example to illustrate that. You may remember this kind of graphical way of representing vectors. So let's say, for example, that we take a vector u, that's 3, 1. We'll go to R2 again because that's easier to visualize, and v equals 1, 4. Okay, let's draw those two vectors on this grid that we have up here. So 3, 1, if we choose to start at the origin, we could go over 3 and up 1, and the vector u then would look like that. Okay, and then the vector v, let's see, that's 1, 4, so we'd go over 1 and up 4. Okay, and so v would look like this. All right, now what would the sum of those two vectors be? And there's kind of a nice geometric interpretation of vector addition in this context. U plus v, if we add the components, we would get 3 plus 1, which is 4, and 1 plus 4, which is 5. Let's go ahead and draw that vector into our picture as well. So 4, 5, here's 4, and here's 5. So it would start at the origin and go up to that point. Okay, there's u plus v. Okay, now what's interesting about this picture is that we can draw in a parallelogram. Okay, so imagine taking this vector v and making a copy of it over here. Okay, that dotted line that I just drew also goes over 1 and up 4. And then we could take the vector v down here and draw a copy of it up here. And notice that u plus v is the diagonal, okay, of that parallelogram. If you look at the parallelogram that's formed by the outer edges here. Okay, and there's a name for this. It's called, I don't remember exactly what it's called, but it's a nice way of representing visually vector addition in R2. Okay, now one last notational point that I want to make here. You might be used to, in previous courses, writing vectors with arrows over them. Okay, maybe something like this, or maybe something like that. I'm going to try to avoid that notation because later in the course, we're going to have something called a complex conjugate, where we put a bar over something, and that's going to have an entirely different meaning than the bar here does when we're talking about vectors. So if you want to, you're welcome to put arrows over your vectors, but later in the course, it might be better if you don't, okay, just because it will avoid some confusion with notation. Okay, so there's our first look at a vector space, and in the next video, we'll look at some more examples.